Okay, 5.1, fundamental identities. So this is also the last chapter that we do in full. So we have a couple sections of chapter 6, but I don't really like how they do it, so we don't really use the book for it, other than for a couple problems here and there. And then we have 2 sections of chapter 9 as well. So we have about 10 sections left of material, and then we're done for the year on new material. So just be aware of that. All right, so jumping into some problems. These first ones say use basic identities to simplify the expression. So most everything is simplifying, obviously, as much as possible. Some of them they're going to tell you to simplify them down to be equal to like 1 or -1, which kind of just means everything cancels out. Some of them are going to tell you to simplify it or rewrite it everything in terms of sine and cosine and then simplify, or leave your answer in terms of sine and cosine. So just be aware for how they're asking for your answer. Not so much that they would ask you for that on the exam as like a question, but they might ask you like, what's the most simplified form, or the stuff that's coming in 5.2, use that stuff to simplify to solve an equation. So just kind of to, let you know where we're headed. So number 10, we've got cotangent of x times the tangent of x. So there's different ways that you can show like what this equals. I could rewrite these things in terms of sine and cosine if that's what these questions are asking. These ones don't care. So I like to think about cotangent as 1 over tangent. So I have 1 over tangent times tangent. Well, tangents cancel, so that's equal to 1. And remember, like, you have to show work with these, and they have to, like, the work has to make sense to get to the final answer. You can't just be like, well, I know that the answer has to be 1 or -1, so I'm just going to pick one and hope I chose the right one. Like, there's got to be some work to back it up to get full credit on these on the quiz.
So is cotangent inverse tangent?
Basically, yes.
Okay.
Not in exactly, because if you, like, because remember, inverse tangent technically only goes from -pi/2 to pi/2. Cotangent goes all the way around the circle. So they are like they're inverses of each other, but not in the sense that it's not like tangent to the -1 is the same thing of cotangent, technically. Kind of, but not exactly. 12, we have the cotangent of u and the sine of u. Now, I'm okay if you switch them all to x's. I don't know, they use different letters and thetas and betas and alphas and whatever else. Like, you can, pick something and stick with it. But anyways, so I'm going to see if I can rewrite something, because obviously I know I want to simplify it, so I want to try to cancel it. So I want to see if I can rewrite cotangent. Well, I know that cotangent can be rewritten as cosine over sine. So I have the cosine of u over the sine of u times the sine of u. So then sines cancel, and I'm left with cosine of u. Um, 14, we've got 1 minus cosine squared of theta over sine of theta. Let's see if we remember. If I see a squared trig function, what should my first thought be?
It'll be a smiley face on the graph.
No.
Pythagorean.
Pythagorean theorem, or not so much the theorem, but I guess the identities. Pythagorean identities. So the one that I notice with this one would be the one that says sine squared plus cosine squared, obviously of theta or whatever, equals 1. So if I subtract this cosine over, that means that 1 minus cosine squared is equal to sine squared. You can lay it there and grab one of those. So I can rewrite the top as sine squared of theta over sine of theta. Sine squared over sine reduces to sine, so the answer is just sine of theta.
Hello.
Hi.
Hey,
Yes. Yes. Not at this moment. Trying to think of where I have kids right now. Actually, yes, possibly. Let me go see if Ethan can run over and grab it. Yep, thank you. Bye. Okay, let me go see him. All right, I want you to just start thinking through this one while I run and see Ethan for a second. Sine squared of u plus tangent squared of u plus cosine squared of u over secant of u. So see if you can start figuring that one out. It shouldn't go off that quick, but if it starts to go dark, somebody hit it so it doesn't lose the video.
Was the vocab test on Friday? What chapters is that? Was it 11 through
10
13?
through 12.
10 through 12.
Yeah.
You're like, you got somebody that's free, and I was like, not in my room. Let me go. I was like, wait, Ethan. Thank you. Okay. All right. Do we have a thought on how to start this one?
No.
So I see squared. So what's my first thought?
Pythagorean theorem.
Yep, Pythagorean identities. So we just said up here, sine squared plus cosine squared equals 1. I see a sine squared and a cosine squared. So what do you think maybe I could do?
1 plus tangent squared.
So 1 plus tangent squared of u over the secant of u. Is 1 plus tangent squared one of my identities?
Yeah.
Yes, it is secant squared. So 1 plus tangent squared is secant squared of u over secant of u. And then that reduces to secant of u. And it's fine to leave this here. Secant is also 1 over cosine, but I would say that the more simplified correct answer would be to leave this as secant. But just be aware of that. If in checking it, you might see that some of the answers are like this or they might be written this way. Just be aware of that. But I feel like since it's already in this form, I would just leave it here.
How would the AP exam have it?
It just depends.
Oh.
You can just lay it there and then grab the filled out one. It just depends. They're going to write things in different ways to force you to see how you did it. But that's why like writing out the steps is good, because in that way, if at any point they stop or whatever, you can see that in the answers. But obviously, if they have multiple, you should go to the most simplified version of whatever they have. But anyways. All right, the next one say to simplify the expression to either 1 or -1. So basically that just tells me that more or less everything is canceling. So 18, I've got the secant of -x times the cosine of -x. So I'm going to use my, what are they called in here? Did I call them negative angle identities or odd and even identities in your notes? Odd and even. Okay, let me make that note here. This is for pre-calc. All right, so in those identities, we have things that show us like the sine of minus theta is equal to minus the sine of theta, and so on and so forth. So with secant of -x, how do I rewrite that one? Yep, just secant of x. And then what about cosine of -x? Yep, cosine x. So then now I can rewrite this secant as 1 over cosine times cosine, and so that stuff cancels, and that's equal to +1. Uh, 22. Secant squared of -x minus the tangent squared of x. So one thing that I just want to mention here is that when I have anything being squared, and this applies with like the identities as well, but as far as like when we get to solving them, secant squared of x is also the same thing as secant of x all squared. So just be aware of that. That doesn't mean that the stuff that's in the parentheses or like the x or whatever happens to be in there is being squared. Okay, that just means that the function as a whole is being squared. So you'd solve it and then square it if you were actually like typing it in to solve it, because obviously we don't just have a button to square cosine unless we square the whole function. So just be aware of that as far as solving. So I would treat this like what we had up here, the secant of negative x, and I would rewrite that as secant of x all squared. Okay. So, or like that's how I would be thinking about it. So this is, the negative just goes away. So this is the secant squared of x, or secant of x all squared, if you want to think about it that way, minus tangent squared of x. So then I'm thinking here, okay, well, does this look like any of my Pythagorean identities? Well, one of my identities is 1 plus tangent squared is equal to secant squared. So if I subtract tangent, I'd have secant squared minus tangent squared. That leaves me with 1, so that means that this has to be equal to 1.
Can you do that again, but slower?
From where?
From whatever you did with the 1 plus tangent squared.
Yep, so same thing that I did up here with the sine and cosine one.
Makes sense.
So I just subtracted tangent. So 1 is equal to secant squared. I'm just not writing that. Minus tangent squared.
Okay.
So I'm just manipulating this that I was given to begin with. So then secant squared minus tangent squared is what I have here.
Okay.
So that's equal to 1.
Okay.
And that happens a lot with our Pythagorean identities, where they give you stuff and then you need to like move stuff around like you would in solving equations to be able to get it to be equal to something else.
Okay.
All right, simplify the expression to either a constant or a basic trig function. They say support graphically. You do not need to do that. You just need to simplify this stuff down. So let's start with 24. So these are going to take up a little more space, be a little more involved. We've got 1 plus tangent of x over 1 plus cotangent of x. So with these type of problems, make sure that you are careful not to try to just cancel something top and bottom when there is a plus or minus or whatever in there with your trig functions. I can't do any kind of like, cancellation just as it sits. So what you're going to find with a lot of these is, obviously I have most of them already worked out so that I kind of know the right path to go. But as far as like my process for how I determine how to rewrite things, there are different ways that I can rewrite things, right? I know that I can rewrite cotangent as 1 over tangent, so that's one option that I have. May or may not be useful to write it that way. A lot of times with tangent and cotangent, the better option is to rewrite in terms of like sine and cosine, okay? So I would typically start there unless I see what we had up here with like, where was it? All the way back up here. I had cotangent times tangent. Obviously, it makes the most sense to rewrite cotangent as 1 over tangent. But within a problem like this, most of the time, I'm going to rewrite in terms of sine and cosine first, because that's going to simplify it down easier in most cases. So I'm going to rewrite the top as 1 plus sine of x over cosine of x, all over on the bottom, 1 plus cosine of x over sine of x. Now, at this point, a lot of people want to do Shepard's favorite thing, keep, change, flip, but I can't do that yet because of that plus in the top, those things being added. So I'm going to need to get a common denominator on the top and a common denominator on the bottom, respectively, because obviously they're going to be different. And then once I have that, it usually works out for me to keep, change, flip, and things simplify down much nicer at that point. So I need a common denominator here. So that means I'm multiplying this 1 by cosine over cosine. On the bottom, I'm multiplying this 1 by sine over sine.
You get a common.
So then on top, I have cosine of x plus sine of x over its common denominator. I'm just kind of skipping one little step here in a sense, over cosine of x. And I'm only skipping the fact of rewriting this 1 as cosine over cosine, technically. But so on top, we have cosine plus sine over cosine. On the bottom, I've rewritten my 1 as sine over sine, so I have sine x plus cosine x all over sine of x. Now I can do Shepard's favorite thing and keep change flip. So we have cosine of x plus sine of x over cosine of x times, so I'm changing from division to multiplication and I'm flipping the denominator, so that's sine of x over sine of x plus cosine of x. So now, even though they're in a different order, I have cosine plus sine, and then on the bottom I have sine plus cosine. They're being added, no sine issues or whatever there. So these things cancel, and I have sine of x over cosine of x. And then I say, okay, can I rewrite that? Well, sine over cosine is tangent, so I have tangent of x as my final answer.
So when we did cosine over cosine plus sine over cosine, why isn't it cosine plus cosine on the bottom?
Because it's like a common denominator. It's like me adding 3 halves plus 2, or like 2 halves, essentially is what I just did. So the denominator stays the same. This would just be 5 halves then. So it's the same deal.
When you multiplied everything on the top by, and really on the bottom too, but when you multiplied everything,
I didn't multiply everything.
Didn't.
I only multiplied to get a common denominator.
right, so you multiplied on the top, right?
I just multiplied this.
You didn't,
If I multiplied it across the whole thing, I would have had cosine plus cosine times sine.
okay, so then how is cosine over cosine times 1 cosine and not 1?
Huh?
Well, cosine over cosine is 1. I rewrote the 1 as cosine over cosine so that I had a common denominator.
So then she could combine the top.
Okay.
No different than if I had, like,
I see.
2/3 plus 3/4 and I needed to get a common denominator.
Okay.
I would multiply by 4 over 4 and then 3 over 3, and then I could combine them. I just didn't have to rewrite this one because it already had a denominator, and that's what I was going to. Since it was just a 1, it's easy. If it's not a 1, then yeah, obviously there's other things I have to do, but most of the time they're going to be 1s.
Okay.
Go away. Okay, that line's apparently, not 1. I was like, that line's apparently just staying there. 26. Secant squared of u minus tangent squared of u over cosine squared of v plus sine squared of v.
I got some water.
All right, I see squared, so where am I going with my mindset here? Yep, Pythagorean identities. So, do I have one that's secant squared minus tangent squared?
Yeah. 1.
Well, you have to manipulate it, but yes. So, it goes back to this one up here that we had in green. 1 plus tangent squared is equal to secant squared. Subtract the tangent, I have secant squared minus tangent squared. Oh, too far. Which is exactly what I have right here. So that means that that's equal to 1. And then do I have one that's sine squared plus cosine squared? Or vice versa, I guess. Cosine squared plus sine squared. That one is also 1. So that means that that's equal to 1. Way less work on that one.
it doesn't matter that the variables are different on top and bottom.
The only reason that they really do that is so that you're not tempted to, I mean, I don't know why you would choose any method other than Pythagorean identities, but so that you don't start trying to rewrite like secant as like 1 over cosine and then start trying to cancel stuff is really the only reason they did that. And because technically within the top and bottom, they don't have to be the same value. Because technically the like v is the same value as like the other one and then you use the same value as the other one. So they're just telling you they don't have to be the same is really all that's showing you. They could be, but they don't have to be.
So like on number 24, is 1 plus tangent x equal to sine x? Like we went from 1 plus tangent x over 1 plus cotangent x, and then we got sine x over cosine x. Does that mean that 1 plus tangent x equals sine x?
Not necessarily. That's just the way that we rewrote it.
Okay.
Um, 28. These ones say use the basic identities to change the expression to one involving only sines and cosines and then simplify it. So anyways, they're just basically telling us which method we have to use here. We have to convert everything to sine and cosine before I can do anything else. So 28, we have the sine of theta minus tangent of theta times cosine of theta plus cosine of pi over 2 minus theta. All right, so first thing I have to do is rewrite everything in terms of sine and cosine. So sine of theta is going to stay. And then I have minus, how can I rewrite tangent as sine and cosine?
Sine over cosine.
Yep, so I have sine theta over cosine theta times cosine theta,
Sine theta.
and then plus cosine of pi over 2 minus theta is what? I don't think so.
Sine.
Yep, sine of theta. So cosines here in the middle cancel top and bottom. So I have sine of theta minus sine of theta plus sine of theta. So that is equal to,
Sine of theta.
yep, sine of theta. (32) Secant squared of x times the cosecant of x over secant squared of x plus cosecant squared of x. So normally when I see the squareds, I'm thinking my Pythagorean identities, but they tell me that I have to write everything in terms of sine and cosine. Now, looking at it, there's really nothing, like these aren't things that just canceled. And what I would tell you is if the denominator with being the two like things being squared added together, if that was like equal to 1 or something, just write that. Don't rewrite them in sine and cosine. Now, these ones aren't, obviously, but if it was already like, you know, say if on the bottom and said it was 1 plus tangent squared, just write that it's secant squared first. Like, don't, yes, ultimately we're trying to change everything in terms of sine and cosine, but if it's something easy, don't make your life harder because 9 times out of 10, they're not telling you which method you have to use, especially when it comes to the AP exam. So, all right, so there's nothing that I can do just outright. There's nothing that can cancel because the bottom is being added, top's being multiplied. And so I need to rewrite this stuff first as far as sines and cosines go. So on top here, secant is 1 over cosine, so I'm going to rewrite this as 1 over cosine squared of x. And technically, just a little side note here, But technically this is really 1 over cosine of x all squared, but 1 squared is just 1, so I'm just putting it down underneath. Okay. So I have that times, whoops, wrong color. Cosecant is 1 over sine, so I have 1 over cosine squared of x times 1 over sine of x. All over, rewriting this stuff on the bottom the same way, so I've got 1 over cosine squared of x plus 1 over sine squared of x. So again, I know there's a temptation to just try to cancel stuff, but with that on the bottom being added, I can't do that. So on top, I don't, technically speaking, need a common denominator. Why do I not need one on the top?
You're multiplying.
I'm multiplying. So that's just going to get smushed together as one thing on the top. Now, on the bottom, though, I'm adding, so I do need to get a common denominator. Okay? So that means that this first one needs to be multiplied by sine squared over sine squared. And then the 1 over sine squared, to have a common denominator, needs to be multiplied by cosine squared over sine squared. Cosine squared. I wrote the wrong thing and said the wrong thing. Cosine squared over cosine squared. There we go. Sorry. I was like looking at it and writing and I wrote the right thing but verbalized the wrong thing. In my head I was like, I think I just said the wrong word. But sometimes I think I do that and I actually didn't. So. Anyways. Okay. So now on top I have 1 over cosine squared of x times sine of x. All over. On the bottom now, the denominator of the bottom is going to be the same, like, is going to be a common denominator. So that's sine squared times cosine squared on the bottom. The top then is just sine squared times 1 plus cosine squared times 1. So that's just sine squared of x plus cosine squared of x. Well, what's sine squared plus cosine squared? 1, so I'm gonna, to not have to rewrite this whole thing, I'm just gonna cross that out and write a little 1 there. So I, technically speaking at this point, have 1 over the cosine squared of x times the sine of x, all over 1 over the sine squared of x times the cosine squared of x. So now what do I do? Keep, change, flip. So I have 1 over cosine squared of x sine of x times sine squared of x cosine squared of x over 1. We're multiplying so I can cancel. So cosine squared and cosine squared cancel. And then the sine and the sine squared. The sine on the bottom goes away. The sine squared, I just get rid of the square. So that means my final answer is the sine of x. We follow that one a little better.
Yeah.
And this is one of those topics where I can work like every even problem for you and you still might get confused when you do the homework because every problem is different. So now a lot of the odds match up with their even pairing. They're like very similar, but just know that it takes, and you probably will have more problems with this section than you normally have for homework because it takes a lot of repetition of how do I use these identities that I know. And you need to be able to use them because if you can't use them in this section, you're going to really struggle in 5.2 when we're verifying identities and having to work down to a certain way. And so part of them telling you, okay, these ones you need to rewrite in terms of sine and cosine is because you need to have that mentality when you go through in the next section and you're solving equations or solving and verifying that things work. Is, yeah, there might be multiple ways I can write it, but rewriting it as sine and cosine might make the most sense. So it's just a process of getting used to it, and so it just takes a lot of practice for these.
I think it's okay now.
Okay.
Let me know if not.
Okay, will do. Thank you. If y'all are in there next hour and you're printing and it's like not, the printer was being weird, so they were fixing it. If it's still not working, can you come back and let me know? Okay.
Okay.
Because I think they just changed out the toner because it was like glitching like crazy. So, anyways, if it's not working, just let me know, and that way I can let him know that he needs to send it up the chain now. Okay. Next thing. Combine the fractions and simplify to a multiple of a power of a basic trig function. So they say, for example, your answer might be something like 3 times the tangent squared of x. Okay, so simplify it as much as possible as far as what we can do. But notice it says combine the fractions. So that means that I need to take and I need to figure out most likely common denominators to combine them. So they're just giving you another tool of how to combine your trig functions and stuff like that. So 34, 1 over 1 minus sine of x plus 1 over 1 plus sine of x. Any idea how I'm going to combine these?
You multiply both sides by -1 over 1, which makes this sign positive. Never mind.
It's just going to say change all the signs. Not a bad thought, just not going to help me get to where I need to get to.
You could find a common denominator.
How?
You could
Multiply by the opposite ones.
Yep, multiply by the opposite ones. In this case, it's kind of like if we think back to our conjugates, when we were doing those, it's kind of like that. It's kind of what comes to my mind when I see these. But yeah, when in doubt, multiply the one on the left by the bottom of the one on the right, and then the one on the right by the bottom of the left. So, that would be where I would go with this. So we're going to be multiplying by 1 plus sine of x over 1 plus sine of x on the left. On the right, I'm multiplying by 1 minus sine of x over 1 minus sine of x. Everybody tracking with why we're doing that?
Yes.
Okay.
Would it be -1 plus sine of x?
No, we just changed. It's just
Okay.
rewriting. It's just this one's going over here and this one's going over here as far as that goes. Get rid of all those extra things. All right, so on top, I have 1 plus sine of x. I'm going to write this all as like one unit as I do this. Plus 1 minus sine of x. All over. On the bottom, I know I'm going to have a common denominator. That's why I'm going ahead and writing this as one big fraction instead. So, this is a difference of squares. Might not look like it, but it is because it's 1 plus something and 1 minus something. So those things cancel out like a difference of squares. So as if it didn't cancel or whatever, then I would just be foiling. But so I have 1 minus sine and sine is sine squared. So I have 1 minus sine squared of x. Okay, because technically I would have plus sine of x minus sine of x as the middle term, which is going away. So if you didn't recognize it as a difference of squares, hopefully you would see that. So now I'm looking, can I cancel anything? Well, on top I see that I have a plus sine of x and a minus sine of x, so I'm going to get rid of those. So that means on top I have a 2. And then what about the bottom? 1 minus sine squared of x. Is that something I can rewrite using an identity?
cosine squared of x.
Yep, cosine squared of x. Sine squared plus cosine squared is 1. So if we have 1 minus one of those, then it's equal to the other one. So then now, am I done?
Yeah.
No. What is the, basically, think about it as 1 over cosine. What's 1 over cosine?
Oh, secant x.
Secant, so then I'm going to put the squared on it, and it's going to be multiplied by the 2 because it was 2 over this. So that means my answer then is 2 times the secant squared of x. All right, I'm gonna hit 38, and then we'll stop there for today. We'll have to pick it up tomorrow. 38. Sine of x over 1 minus cosine of x plus 1 minus cosine of x over sine of x. Any ideas on this one?
Multiply the whole thing by each reciprocal.
I think you're kind of on the right track, but I don't think you're saying the right word.
Can we just
Tell me what you want me to write.
So basically, like, multiply that first one by the opposite, or by that one.
By this?
Kind of like what we did before, but like a whole thing.
Like that?
Yeah.
Good answer. All right, and then what about this one over here?
And then it would just be cosine instead of sine.
we do 1
1
minus
minus.
cosine
It's got to be the denominator of this one, so it's got to be 1 minus cosine over here. Yep. The only difference, which is why I said like the reciprocal thing isn't, is because these are opposite now. But this is just a sine of x. That means I've got to just multiply by sine of x. Over here is 1 minus cosine, so I've got to do that there. You can just sit right there. All right, so on top I have sine squared of x. Oops, let me change colors back. And then over here, this is actually like a perfect squared trinomial. It's not a difference of squares. So that's plus 1 minus 2 times the cosine of x plus cosine squared of x all over on the bottom. It kind of can go either way. Sometimes I leave it and I don't multiply it through. Sometimes I do go ahead and multiply it through. Let's not for the moment and see if it works out, and then I may have to go through and multiply it. So I'm going to leave this as the sine of x times 1 minus cosine of x on the bottom. Okay, so like I said, sometimes I multiply it, sometimes I don't. I sometimes wait because a lot of times we end up having to factor it back out when things cancel. It just like makes it easier. All right, so on top, I see a sine squared and a cosine squared, so what might I do with that? Yep, sine squared and cosine squared equal 1. So I have now 1 plus 1 minus 2 cosine of x on top. So that's going to be 2 minus 2 cosine of x over sine of x times 1 minus cosine of x. So is there anything else I can cancel?
Factor out of 2.
If I factor out a 2, then I have 1 minus cosine of x, like on top times 2. And then I have sine of x times 1 minus cosine of x. Now can I cancel anything?
Yeah.
Yes, I can cancel the 1 minus cosines top and bottom, because multiplication is happening. So I have 2 over sine of x, which is what's 1 over sine of x?
Over sine of secant.
Cosecant, so that's 2 cosecant of x.
How did we factor out the, what do you mean by, how did you take out that 2?
Because there's a 2 in both pieces, so I can take it out.
So when you took out the 2, why did it become 1 minus instead of?
Because it's multiplying, so it's like distributing it back. No different than when I have 2 minus 2x, and I factor out a 2, and I have 1 minus x left. All right, we're going to stop there. I'm not going to give you problems today. We'll finish up this stuff tomorrow. Not a ton left. So like I said, every problem's different, so it's just going to take practice getting used to using those identities, but make sure you are, starting to study those, because most likely next Monday or Tuesday we'll be doing the little quiz on the identities.